Okay, good. So fracture toughness is the next topic. So fracture toughness is different than toughness. I'll highlight that on the next slide. Fracture toughness is the resistance to propagating a crack. Okay, so similar to the material we just studied for this. So the three modes of crack propagation that are known are mode one, where we have an opening or a tensile mode. So top half of the material just moves away from the bottom half of the material, and we have an opening that leads to our crack with stress concentration happening at the tip. Secondly, there can be more of a sliding mode. So perhaps the top half of the material is shearing past the bottom half of the material. That's a mode two, a sliding mode for the propagating an ultimate crack. And the third mode is a tearing mode, where one material is moving to the back and another material is instead moving to the front, and we are tearing the material to propagate that crack through it. The type 1 mode is more easily handled by us mathematically at this point, and so it's characterized by a constant that is called the K1C, given that we are a mode 1 condition. So the K1C is again going to represent the actual sigma value to propagate that crack relative to the amount that is actually applied. So let's look at some K1C information, a constant that represents the resistance to crack propagation. Just to remind you again, the resistance to crack propagation is not toughness. So fracture toughness is different than toughness. Toughness is, of course, the area under the stress-strain curve. And fracture toughness is that resistance to propagation. And we'll develop an equation and understanding for that. So fracture toughness. Our K1C values, some of which are listed here, are calculated from the following information. So there is a dimensionless geometry factor, which again is characteristic of the conditions of the test specimen. If it's large relative to certain surface flaws, then this geometry factor of 1 can be applied. If the dimensions of the sample approach the dimensions of the surface flaw, y will differ. Okay, so for the majority of our questions, we'll be able to handle a y of 1. Okay, so the K1C also goes with the stress at failure. So here we have sigma, which is the stress at failure. So it's the final stress value in our stress-strain curve, or the stress that has caused failure. Okay, it also multiplies through by root pi times the length of the surface flaw. Okay, so again, at A is the depth of that surface flaw from a half ellipsoidal model to represent that. So we can think about what the unit should be. We know that stress is force per cross-sectional area, so that is newtons per meter squared, which is of course pascals. Typically these values are high, so megapascals are typical, so there might be a meganewton there. And ultimately we have the square root of an A dimension, which is a distance dimension, so we're expecting root meter for the last part of the units there. So K1C values, which represent fracture toughness values, are going to have units of megapascal root meter. Very complex kind of set of units. Alternatively, in non-metric units or non-SI units, you can have similar information where KSI, kilo pounds per square inch, root inches would be used there. Okay, so here you can see the K1C values for alloys and steels, concrete, and even plastics. And you can see some of the most resistant values are characterized by high K1C values, and they're found in the cases of alloys and steels, whereas concretes and other materials have lower K1C values. Okay, this equation, by the way, has been developed under an assumption called the plane strain condition, which has a few details in it. It tells us that the K value is independent of thickness of the relatively thick specimen. So we touched on that earlier, that we're using this to represent very large specimens with small surface flaws and small cracks. The plane strain condition is also applies with the condition that the load operates on a crack such that there's no strain perpendicular to the front and the back of the faces of the crack. So as we see in our diagram earlier, we are not applying load on the front or the or back of the crack, but rather focused on the tips where small plastic deformation occurs. And so there we have small plastic zones at the crack tip is where most of the deformation occurs. So those are the conditions inferred by using this K1C equation here, which again is calculating fracture toughness, which is the resistance to crack propagation. Okay, and so here you see some values. We saw some on the previous table, and just kind of better rank them if you want. So the higher you are up here, the more fracture toughness you have. And so steels, alloys tend to be the most resistant to crack propagation. Some composites and fibers are competitive. So things like carbon fiber with parallel fibers to the stress direction do well there, as well as some other kind of ceramic composites as well. And then things like pure polymers or pure ceramics tend to be kind of lower materials, including glasses. Okay, so let's take a look at a final example, and we'll call it a day. So here we have a high-strength steel, which has a yield strength of 1460 megapascals and a K1C of 98 megapascal root meter. We're asked to calculate the size of a surface crack that will lead to catastrophic failure at an applied stress of half of this yield strength. Okay, so take a minute again to develop an approach to this question and attempt the question. And when you've got an answer, resume the video and we'll see what you got. Okay, so we saw that our K1C equation was equal to a geometry factor close to 1 times the stress it caused. We need to fail the material, so we'll put a little f on that to make it obvious, times the square root of pi times the depth of this surface crack. So what we're asked to do ultimately here is solve for A. So let's do that.